Welcome back, everybody. So our next speaker is currently an assistant professor at the CSE department at IIT Hyderabad. He received his PhD in computer science and engineering in 2012 from IIT Kanpur, and then afterwards served as a postdoc research assistant at the University of Oxford for 3 years. He's also served as an assistant professor at IIT Guwahati. He's interested in constraint programming, formal verification, and program analysis. Very heavy stuff. He's worked on projects like LLOV, which is a static data race checker for OpenMP, GPU repair, which is a tool that proposes fixes to data race and barrier divergence errors in CUDA and OpenCL kernels. So please join me in welcoming Dr. Saurabh Joshi for his talk on contract programming, what, why, and how.
So first of all, I would like to thank organizers for inviting me for this talk, and happy Independence Day to all of you. So this is it's a primarily CPP India, and it's a C++ focused conference, but I'm not really a C++ expert. So when the organizers approached me first, I spent about more than 15 years in trying to reason about safety of systems. That how can you ensure that systems are safe, right? So in the abstract, you might have seen these words that how as a programmer you can ensure that nothing can go wrong, and the answer is I don't know. It's the holy grail, right? It's a quest, and I'll tell you that why it's a very difficult problem along the line. So I'm, yeah, as mentioned, I'm a faculty at Department of CSE, and primarily I sort of work on program analysis and reasoning about programs, how programs behave, and things like that. So let's, without further ado, I think let me just jump into this one. Now, before that, there is going to be a logical break during my talk. So I'll answer questions only at that point of time, but you can post your questions in the Q&A, and I'll take up questions during that a brief pause between the talk. Okay, so this is usually a nice exercise. Usually, when I give it to my students, show a code like this, and I ask them that, is this program correct? Right, and on the face of it, it looks like everything seems fine, right? Nothing is out of the ordinary. And then, now please note that I'm not going to modify the program itself, okay? Right, I mean, it feels that this should compile just fine. It is, so this program is correct. And the only thing I have to do is add a comment, right? And now, without actually modifying the program itself, I made the program incorrect, right? So that's the first lesson, that before we, sort of start our quest on whether the program is correct or not. So very important step is to first define what do we mean by something is correct, right? So it's a nice little example that it's my pet example that I often use during my classes. Right, and this is what contract is, a code contract is all about. That you try to formalize and define in an unambiguous manner that what do you mean by the program is correct. Now, if we go to the history of contracts, then actually the concepts, or rather the ideas, concept I can't use anymore because within the context of C++ now it has a different meaning. But the idea of contracts came way before C++ itself. I mean, it came, so these two gentlemen as shown in the picture, Robert Floyd and Sir Tony Hoare. So they independently proposed a system of axiomatic reasoning about correctness of programs. And so they are the ones who we can thank about this very impactful research on the program correctness. Right, and I mean, especially the gentleman on the right, Sir Tony Hoare. So he is the one who invented the null pointer or the null reference. And in one of the conferences, he himself mentioned that this is my $1 billion mistake. Right. So yeah, I mean, he's the one who sort of gave both the illness and the medicine. But but yeah, so he has also a Turing Awardee, which is a Nobel equivalent in computer science. Sir Tony Hoare he got Alan Turing Award by ACM for his very impactful work on the program correctness. Right, and then so this is, I mean, when these work started, it was primarily about sequential programs. I mean, this whole work, and then there is as the architectures evolved, and we have like a lot of varieties about programs, and then there are separate. There is another landmark work in 1976 which talked about that how which kind of defines the system of writing these code contracts and what do they mean and how can you define the correctness for concurrent programs. But then there was a huge gap, and in 2001, this John Reynolds and Peter Vaughan, they gave a systematic way to prove that whether the heap manipulating programs, when you have dynamic memory allocation, deallocation, things like that, and whether you can prove those kind of programs correct. And then there are a lot of other variations that followed, but I think that these three work, one is this, and are these three works what lays the foundation of these ideas of program correctness and contracts and things like that. Right. So what is a code contract? Right. So if I have to say what is a code contract, I would say that it's a formal description, and the formal is the one word that I would like to emphasize. Is a formal description of the set of states or behavior. So in this talk, I'm not going to focus on the behavior, but it's a formal description of the set of states of program or program fragment, which defines the correctness of the corresponding program or program fragment, right? So what does it mean is that you want to say that at a given program point, what is the truth that should hold, right? What does my program state, what kind of program state should my program be in for the program to be correct at a given program point? But in general, you can actually, instead of a one program point, you can say that I want certain kind of behavior as a sequence of program points, and it has to behave like this. But today I'm not going to talk about the traces or executions, only the contracts at program points, well-defined program points. And the relevant quote is, by Bertrand Meyer, is a very impactful work that he has done, Bertrand Meyer. And he's the one who is creator of Eiffel programming language, which have sort of native support for code contracts. C++ still does not have, as part of the language itself, code contracts. Whereas the very first, to the best of my knowledge, the very first proposal in front of the committee that came for code contracts came in 2006. So it's about 15 years. And then there has been several other attempts at proposal discussing in the committee, etc. But those proposals, for whatever reason, did not make it. Right? But I think this statement that our field needs more formality. Now, many people, I think there are different thoughts. People think that you don't really need mathematics to study programming, etc. I would sort of humbly like to differ that knowledge of this formalism and mathematics does indeed help in reasoning about how the program behaves. Right? So let's move on. And it is not that because we don't know the formal notion of code contracts, people have not been using code contracts we have been using it. It's just that we don't know that, okay, this is called code contract, right? So for example, if you have a code fragment like this, so what does that assert statement convey? It does tell you that as a programmer, what I want is that when my program is executing and it reaches this line number 3, I want that my program should be in a state where this pointer n should not be a null pointer. So this is contract. It is formal. Why? Because the semantics, this condition, it has a well-defined semantics as per the programming language. Right? So this condition that L is not equal to null pointer because it is a well-defined symbol. It's not written in English language. I'm sure that those who are working in the software industry, they would know that specifications written in English language, they are often ambiguous. They are likely to be misinterpreted and things like that. So this is a very simple thing. Just an assert statement is a contract that you want some truth to hold for the program state at a given program point. So let's a little bit more understand about state of the program and what the programs actually are, right? So let's see that what is a program state. So program state is nothing but, I would say, values of all program variables. It's a little bit more in addition to program variables. There are other variables also play a role, but for a moment, for the sake of simplicity, let me just say that at a given instant, I would say, so instant is an abstract notion of time. That what is the value of all the program variable when you just freeze everything and at a given snapshot? That is a program state, right? And so even though our programs have this, multiple states, so imagine that my program has a single variable called int. Assuming it's 32-bit signed integer, it has 2 to the power 32 possible states, right? So just a one variable code, it has these many states, right? And if I just have an array of 100 elements, this number quickly becomes 2 to the power 3200 possible states. Now, just to make it clear that how large is this number, this number is so large that if you divide our entire observable universe into small cubes of Planck volumes, Planck volume is the smallest physical volume that is possible, right? And so this number is far greater than that many number of cubes. I'm not even saying subatomic particle or anything. I'm just saying that we just divide entire. It's way bigger than the universe, right? But this is very common occurrence that you might use in your program array of size 100. And now what we are talking about is that we want to reason about the system that has the number of states which is kind of larger than the universe, right? And you want to reason about such a system, that is this system safe, right? So it's a very sort of difficult thing. So let's say, for example, this is our program fragment, just a declaration of x, and then I do x is equal to x plus 1. Now, after line 1, since x is not initialized, x can be in any, it can take any possible value within the signed integer domain, right? So your system, after line number 1, can be in any of these 2 to the power 32 possible states, right? So what are those states? It could be either x is equal to int min, either x is equal to int min plus 1, int min plus 2, int min plus 3, so on and so forth, up to x is equal to 0, all the way up to int max. And so when I talk about this line number 2, which is x is equal to x plus 1, and now I say that does x is equal to x plus 1 is correct or not, it does not, in and itself, you can't define the correctness, right? So you have to talk about that on what set of state it is applied to, right? So as you can see that, this is fine, that if you apply it on int min, it's going to work fine all the way. But what happens when you apply it on int max, right? So that means that our program, the one-line program, x is equal to x plus 1, what they are actually, what they do is they are state transformers. So they take a set of state, as you can see on the left-hand side, and they transform into another set of state, which is there on the right-hand side, right? So programs are actually state transformers. You take some input set of states are there, and then you take it somewhere else. Right, and you know that if you execute this particular program in a state where x is int max, then it's a problem, right? So the correctness of your this one-line program, it depends on basically what is my input state here. Right. So it is going to be correct for all the other values, which I'm denoting it as x is strictly less than int max. And it's going to end up over here somewhere where I know that x is going to strictly be greater than int min because I'm adding at least one element. It is going to be incorrect if my input state is this one. So that gives a notion, obviously. So I mean, you can refine this further by saying that, okay, this is a very loose statement saying that x is greater than int min. I can say that x is exactly equal to whatever its old value was plus 1. Right. So this is it's a much more refined or smaller set in that sense. It's a more precise description of the set of state your program is in, right? And that's why this circle, I made it smaller. Right, so these contracts, so I'll say here that this is a precondition. So for this program, it's a one-line program. This part is called a precondition. So precondition means that if my program is in a state which is inside this particular set, the set is described by a condition. So any condition, you know, in your if statement and while statement, any of the predicate that you write in your program, all of them, what they do is that they describe a set of state. So precondition is that, okay, it states that for this program to execute correctly, this one-line program to execute correctly, the input state has to be inside the set of states that is described by this precondition, right? And then when this program terminates, and hopefully this will, it's a, you know that by the semantics this will terminate, the program will guarantee that you will end up, your program will end up in a state which satisfies the post condition. Right, so it's like, you know, I mean, since this is Independence Day, many of you know that, you know, tum mujhe khoon do, main tumhe azadi dunga, support by Netaji Subhash Chandra Bose. So similarly, you can think about that the correctness of a program, it depends on these two things, that you give me a state which is inside a precondition, and I guarantee as a program that when I terminate, I will leave the program in a state which satisfies the post condition, right? So this is a contract, right? The contract to the user of the program. It could be a program fragment, which is a one-line code, which is described over here. It could be a function. It could be a lot of other things, right? So we know that these conditions are sets. In the program itself, they transform one set to another kind of set, right? So it's a relation between these two sets. Now, so we know that there is a problem, right? If I execute this program when this is not really initialized, there could be potentially signed integer overflow is an undefined behavior. And imagine that you are running a million tests, which is drawn from uniform distribution. So uniformly random, you just pick random numbers within the domain of signed integers. You run this program a million times. There is less than 1 in 4K chance that you will actually find this problematic case, right? And you might think, okay, fine, big deal, right? I mean, it's x is equal to x plus 1, right? So that's okay. But what if that x is equal to x plus 1 is used in this particular context? You can see the code. Yes, I mean, I kind of like to make things dramatic, right? What if that x is equal to x plus 1 is something on which the safety of the world is dependent on, right? So if you know, if it overflows, then just launch the nukes and destroy the world, right? Because you don't know that even something as small as just adding 1 to a number, what repercussions it's going to have, right? And to make matters worse, now that, you know, most of us have moved to architectures with a 64-bit, right? So imagine that I'm using a 64-bit signed int. Even if you conduct a billion tests, billion with a B, the probability that you will find this problematic case is less than 1 in 16 billion, right? I just let that sink in, that how hopeless is this scenario, right? When you try to test things, right, in the conventional testing sort of. And if you wonder that this is a hypothetical scenarios, it's not, because the world has seen so many disasters that is caused by very small software errors. So Ariane 5 sort of space shuttle blew out of the sky a few seconds after the launch because of type narrowing. Mariner 1 also sort of blew out of the sky because there was a missing hyphen. And there are many other sort of cases. For example, Nest thermostat bug. So this Nest smart home system, it had some bug which caused battery drain, and so that means that even in the cold area, people who are living in North America, etc., the thermostat didn't work properly. So the temperature of their house actually went like very cold because it wasn't working properly. You can actually freeze to death. It didn't happen, but there is a possibility this can happen. Threat 25 is the case about a medical imaging device, which because of a data race, it gave fatal exposure to many patients. And I think there were a few casualties. People actually died because of over radiation, right? And this, it's not a very small list. So this particular professor here has compiled this long list over here from including from these modern ones like 737 MAX 8 problems and this various problem, this 2018, 2010, and you say, I think I'll leave it to you. The slides will be available. These are all very interesting, and these are all. It's not that only the software was the one problem; it was part of the problem. A lot of other things had to go wrong, but certainly we can do better as software engineers and developers. So these are another sort of set of list. You can browse at your own leisure. In particular, this one. So this is a very nice description I like. So I'm just putting this link over here. That this is something where people tried to sort of fix things which could have done by a physical redesign of the airplane Boeing 737. Instead, they tried to fix it using software. Now, uh, so the approach to safety, if you look at mechanical engineers or civil engineers, etc., they use physics, and the laws of physics are not something that can be broken, right? So they use physics to embed safety in it. So if I recall correctly, so Otis was the this elevator manufacturer when he first invented the elevator, and to show that how safe the elevator is, what he did was that he put himself in the elevator and then asked people to cut the rope, cut the cables, right? And the idea is that it is a tension in the cable that is preventing the brakes from applying to the rail of the elevator. So the moment that tension is gone, the brake will automatically be applied to the rail. So the elevator will come to a safe state on its own. Right, and it's the same principle behind the dead bin switch. Please look up how the seat belts work. When sudden deceleration happens, or how airbags work. Everything, if you think about it, is that they use physics to get this safety features. But unfortunately, as a software engineer, our approach to safety is I would say relatively much more casual as compared to other engineering disciplines. And this is just my opinion. I don't want to sort of offend anyone, but right. So let's see, right? So when we try to ship out software, what we try to do is that we try to test things. And how does the testing go, right? So this black circle that you see over here, imagine that that is the set of all inputs your program can get, right? And so in the testing, what happens that you pick one test case and then you run it. It continues to run across various stage. And when the test finish, your test says that, okay, the test passed, right? Then you say, okay, let me pick another point, right? And you again run your program, the test passed. Let me pick another point. So you can keep on doing it. As I said, you can keep on doing it a billion times. And then you say that, okay, fine, right? And I've tested my code a billion times, all the tests are passed. Let me just go happy, go home. And then when your system is in production, when lively running, this happens, that you did not test for one particular input state. When you run your system, it ends up in something that leads to an error state. It's a disaster, right? So there is a fundamental limit to this conventional method of testing things, is that just because the tests are not failing, you can't really guarantee safety, right? So so let's see, right, that what do we really want? Ideally, what do we want? So ideally, what I want is that instead of reasoning about one input state and how the program behaves, one input state at a time, ideally what I want is that give me all the input states, and when I take this step as a program fragment, as a transformer, it's going to end up in this entire set. So I want to compute this entire set. As I execute my program, at all point of time, what I want to do is that compute all possible states your program can be in, not just one. This is ideally the world. This is ideal scenario, right? And if we can do that, then when I know that finally when I compute, yes, there will be a lot of states which will be error-free state, but in the entire large set, there will be set of state which will be erroneous states. And so we know that the system is not safe. Right, but here's the problem. And what is that problem? The problem is that computing sets like this and reasoning about this program is undecidable. And that means that there are programs for which this computing this exact set of reachable sets, it's impossible. It's a mathematical impossibility is proven, right? So you can't really beat mathematics. I think just there was a discussion about this Turing completeness. So something is Turing complete, that means that there would be undecidable instances. Right, so I mean, just to give a context, like so for example, C++ type system, because it is Turing complete, that means that there could be programs for which the compiler may not be able to finish or terminate the type checking or the type inference part. And that's what I think I asked the question that because yeah, I don't know how compilers exactly do that, but somebody then answered that it has some kind of you unroll it so many times or timeout mechanism. So the mathematical impossibility. In fact, lot of questions about program behavior are undecidable. So that means that you can't do this statically. You can't compute this exact information, right? Okay, so what to do, right? And the theoreticians typically, okay, it's undecidable, done, let's just go home and sleep. But we are engineers, right? So even though it's impossible, we say yes. So undecidability means that there are some programs for which you can't do it, but it does not mean that there are no programs for which you can't do it. There will be a lot of programs, right? That's why compiler exists for C++, because otherwise people will say, hey, you know what, C++ type system is undecidable. Let's just go home. Let's not write compiler. But that's not how people deal with things in practice, right? So that is one possible approach. That let's try to put on the best effort basis that how much we can actually compute these exact sets for the programs for which we can do, right? And I'll talk about, there are actually some tools that actually do that, do compute these exact sets, but yeah, I mean, there are some other problems. The other alternative is that instead of computing the exact sets, what we can do is that we can compute over approximate set, right? So that means that when I move from this to this, instead of only computing this black part, I'll say that how about I compute this larger part? And you might think that how making over approximation make things simpler. So if I give you an example, x greater than 0, right, for a signed integer, it represents 2 to the power 31 minus 1 values, right? So that's the size of the set. But if I say x greater than 0 and x less than 10, right? So there are only about 9 values in this particular set. But you see that the description is longer for the set with 9 values, whereas a description is much smaller when it's a larger set, just x greater than 0. Right? I won't go into detail that why this kind of symbolic computation, there is no correlation between the size of the set and the size of the description, right? But many times this is simpler. You're computing over approximation might make problem a little bit simpler, right? So what I can try to do is that try to do this over approximate computing and still reason about program that, hey, can I reach in my set of reachable states? So now it is these yellow sets that I'm computing. Does it intersect with the red ones? If it intersects with the red one, that means that there is a possibility something is going to go wrong. But there is no free lunch, right? So first thing, the good thing about over approximate set calculation is that if, for example, if your program is or system is indeed safe, right? Even with the over approximation, if it does not intersect with this red, then you can certify that the system is safe. You remember that when the testing, if all the tests are passed, you can't guarantee that the program is safe. But when you do this kind of static reachability analysis, even if it is over approximate, and if you don't end up intersecting with this red set, which is your error set, then you can still say that I know that my program is going to be safe, right? Because it does not, if it does not intersect with the yellow one, it surely is not going to intersect with the green one, right? But since there is no free lunch, something like this can happen, where the red one only overlaps with the yellow part, right? So this green is the exact reachable state, but because you did over approximate calculation, you might end up in intersecting the red one. So this is a false positive, right? Because your analysis might say that, you know, your program can go wrong, but in reality it may not go wrong because this green one is not intersect with the red one, right? So yeah, that is so in the testing side, when something goes wrong, you definitely know that something is wrong, right? The test passes. Whereas in this approach, when it says that, you know, everything is okay, you know that everything is okay, right? With the condition, terms and condition apply, which probably I'll talk about. So it can guarantee safety. You have a certificate of safety that, you know, your system is going to run just fine. But you have a chance that you might end up in a false positive, right? So this, I think that I mentioned, the very important advantage about testing is that it scales well. Even if you have hundreds of millions of lines of code, you can still test, you can still run, etc. Even the state-of-the-art tools that does this static reachability analysis and computation of the sets, they don't actually scale very well, especially when you try to do it in a precise manner, right? Also, testing is well understood by the community, whereas static reachability is not as well understood and as accessible to the larger community, right? But the testing does not guarantee safety. Static reachability analysis, it can guarantee safety of your software systems, right? And so now let's come to the contract, right? So as I said, the idea of contract actually predates C++ and a lot of other programming languages. So this is the precondition over here on the left hand side. I hope that you guys are able to see the cursor, my pointer, mouse pointer. This is your program, and you end up on the right hand side, right? So if you are able to prove, I give the precondition and the postcondition, and if you are able to prove that yes, starting from this, you will end up over here, then you know that this program is correct. Similarly, for another function, let's say f2, you know that if you as a programmer specify the precondition, the postcondition, and let's say assuming that there are some static contract checkers are there, if they can establish this relation that yes, it is indeed true that when you start from here, and if you terminate your computation, then you will end up over here. Now, how do you compose this thing? So as I said, that the building blocks are that you start with a small program fragment. And the way you sort of build, talking about larger and larger program, is that if you can show this one, that the post condition of the previous statement or previous program fragment is inside the precondition of the next one. Because then you can guarantee that when you're going to start from here, you are going to end up in the last one. Because otherwise, you can't guarantee if this thing is not completely inside the precondition of the next one, right? And using this technique, you can sort of keep on doing, keep on composing this proof, and the set of states are computed on and on and on. Now there are sort of other kinds of invariant which I haven't talked about. So there is a problem that there is something that is called a loop invariant, for which finding a precise loop invariant itself, that is also an undecidable problem. But so that is how the static checkers can reason about loops, right? So in practice, there are static checkers that are available for programs. For them, if you as a programmer, you provide the contracts, it is easier to check rather than just synthesizing them. In theory, both are sort of undecidable. But in practice, this is easier. And especially, so even myself, who has designed a contract checker for C, right? Our main concern is that the programmers do not write assertions in the program. So if we don't have the contracts, we don't know against what to check the program for, right? So against what specification we should check the correctness, right? So that is why it is very important to specify as many contracts, assertions, invariant as you can in the programs. And also, when you have multiple contracts at various program points available, you can do in parts, right? Okay, you check between these 2 points and these 2 points and these 2 points, etc. And then, as shown over here, that if you can show that the post condition of the previous one is inside the precondition of the next one, then you can compose. This does not always have to happen, right? It's the same reason why even if you do unit testing, you still have to do integration testing. So it's the similar reason, right? So now there are a lot of static checkers are available. Some of them scales relatively well, like CPP check and Clang static analyzer. So links are there. These are clickable links. And these take just a general guidelines that what does it mean to have correct programs, like you have some array index out of bound, or some kind of memory safety, or API usage are correct or not, or whether you have overflows in certain like fashion, etc. Things like that. The listed below are the checkers which can take assertions, right? And I only listed, so a lot of checkers are available. I only stated checkers which can take some amount of C++, some amount, because the problems, I myself have worked on one of these tools like CBMC, and the problem is that the C++ now has so many features that formal modeling and computing this set is just that the community static, those who build these static checkers, they are not able to catch up the speed at which the C++ is adding you a new feature, because the formal modeling becomes very difficult. Right, but for C, you can try these tools, and there are many other tools for C and Java. I think that there are more tools available. You can write arbitrary assertions as you can specify in your programming language, and these will be able to check that whether there is any possible scenario or behavior under which your program can fail. But they don't scale well, right? So if you have very deep loops or very large code base, etc., this not necessarily it will terminate in time, right? And some of them are bounded checkers. That means you have to tell that, okay, unroll the loop so many times and things like that. Links are given for all of this. PVS Studio is a proprietary one, and MCP is there's just a paper, so the NASA uses this, but I could not find the source code. But all others are open source tools. And now let's move on to the dynamic checking, right? And especially in particular for C++, I'll show you some examples. But I think at this point of time, because there's a logical pause if there are questions, couple of questions, I'll quickly take those questions, and then I'll show actual code about dynamic contract checking in C++.
Yeah, Saurabh. So there's just one question here at the moment. Is contract programming fulfilled by test-driven design or unit testing?
Yeah, it sounds very similar, but no. I would say that both of them should be done. I mean, I don't think that one precludes the other. Yeah, I mean, you should have both. Just because you have TDD or just because you have contract does not mean that. If you have contract, does not mean that you shouldn't do testing. If you have testing, does not mean that you shouldn't write contracts. Uh, right. Any other question, or I can
Yeah,
go
just one
some
just popped up.
examples?
Even exceptions can be used as contracts, not necessarily assertions. The question is about specifically exceptions.
Can exceptions be used as contract? I mean, that's a good question, but the thing is that, I mean, when you say, okay, throw an exception. Now, see, many times just because something is an exception does not necessarily mean that for your program per se it's a bad state. Many people write code like that, so I don't think that that is necessarily kind of true. Uh, so contracts, think of it this way, that basically the moment the contract is violated, from that point on, like the program is not correct. In fact, there was what I read, that there was a huge debate within the committee as to that when the program contract gets violated, what should be the behavior, right? Because the moment contract gets violated, since that is the one that defines the correctness of the program, and since the implementation don't have to do anything, implementation means the compiler, etc., will say that, well, I mean, once the program is incorrect by its own definition, then you can do anything, etc. So there is a huge debate. So I don't think that yeah, exceptions can replace contract. That's my just personal view. Uh, right. So many times, for example, file not found, people use exception, but that is something that you expect that, yeah, there is a possibility, and people use it just to change the flow of control, but not necessarily it's a bad thing for your program. Yeah. So yeah, I
Okay,
think
we
that
have more
I can go
questions,
through the
but I guess we
examples,
should.
and then if there are, yeah, I think yeah, we'll take in at the end. So
Yeah,
I'll share.
less than 20
Code.
minutes now. Sorry.
Let me. Yeah, sure. Okay, so is my editor visible? VS Code.
Yes,
Hello.
it is. It is.
Can someone please
Yes, it
confirm
is visible.
if yeah. So this is directly taken from actually Boost contract library. So there are since the language does not offer contract facility natively, many libraries are out there, but I believe that since it's a Boost, I rely on Boost more than any other library. Right, so there are three parts, and there are limitations also I'll discuss, right? So as I mentioned, right, so this is the same example that x is equal to x plus 1. That's what we are trying to do over here in this method. The signature, if you that you are taking the reference and you are returning an int, but what you are returning is the old value, right? So you are changing the value of x, you are incrementing the value of x, but you are returning the old value. So remember that that is the implementation. Now to capture the old value, and that is one nuance right here, right? That so ideally you should have like completely freeze so that you have a snapshot, you know exactly what the program state is, and you read the entire state and then check that in that particular state whether your contract gets satisfied or not. And in the post condition, that means that when this code finishes executing, you want to check the post condition. So you need something, what was the old value, right? And for which this Boost provide this facility for, Boost contract old of X, and you take this pointer. The problem is that this does not work if your object is not copyable. Right, so this is the limitation of Boost library, and I believe that this probably will be limitation if even if the contract comes into this thing that if you have types defined which are not copyable, then how do you compare something with the old value, because you want to reason that from old to new this is the transformation, right? So that is one challenge. I think there is another macro that Boost provides, which you can use old of some, non-copyable or something, in which case it will return the null pointer. But that's not the point. So this is problem number one with the, at least in this library, is that, yeah, I mean, since there is no snapshot for non-copyable thing, this does not work, right? Then I can define this functor, which Boost provides, and you pass a null array lambda and say that, okay, so this is my precondition. Okay, I'm inside the precondition, and I say that if x has to be strictly less than the int max, so this is nothing but int max, right? So you remember that that's what our deal was. That this is my precondition. If you give me an x which is greater than this, then the precondition fails. My post condition is what? The post condition is that x is 1 greater than the old value, and the result is exactly equal to the old value, because that is how this is implemented. And Boost also provides that in case of an exception, do you want some contract on the state of the program? So it says that in case of an exception where the program control does not exit via this return loop, but because of the exception, in which case you don't want the x to be changed, right? So these three things are provided. If it is a normal function without, it's not inside any class or anything, right? Okay, so and in the main, it's just that, okay, I'm just doing x is equal to 5. I'll print 5, then I'll use this increment, and then I print again. So let me show you how it works. I think it's already compiled. So right, so initially it printed 5, and then this is the new value because x has changed. You have taken a reference, and this is all fine, right? But now let me just uncomment this where z is actually int max, and now I try to print. I want to increment z, and let's see that what happens, right? So okay, yeah. So now if I do this, you see that it says that, okay, the precondition assertion on line 28 is violated. It could have provided better diagnostic as to for what was the value of x, etc. But at least I know that here this particular precondition is violated. So so there you go. And also about the post condition, right? So now again, let me just comment this out. And imagine that your implementation isn't correct. So let's say that I do this. Right, which is certainly an incorrect implementation because I'm not really implementing x. And now if I compile and run my program, then it says that, right, our post condition is violated on line 31, which is this one, right, that this particular condition is violated. That's what it says. Right, so this is sort of, okay, sort of fairly simple way to use it. There are a few notes in this Boost library. So the documentation itself states that if you want to use the version with lambdas, which is easier to use version, then you just need this particular header file. You just download whatever the latest Boost is, and you get this null array lambda. But there is one more point, right? So here, this is the modification done by me in the example given by Boost. It just does a capture via reference, right? So this is what it does. The problem with that is that that keeps x to be mutable even inside the body of your contract, right? And typically what you want is that you only are supposed to read the program state, you are not supposed to modify it. So ideally what you want, and I think that this is a very desirable feature even for Lambda, is that there should be a capture available like this, that you capture everything in the context by reference, but as a const reference so that you don't modify. So this is ideally what you want, which is not there. And I think even in the latest proposal that is there, they are saying that this constness cannot always be guaranteed for various reasons, etc. Right? But yeah, I mean, if for example you want to use it, make sure that you try to capture it as const and then use it inside your contract so that you don't accidentally modify x. Now see, one question, you think that the computation that I'm doing here is almost about the same as the contract checking, right? I mean, one of my students asked a question that is almost as if I have to recompute everything just for checking the contract. But this not necessarily always the case, right? So for example, this is another code. This is the implementation. It's a factorial. So you take x, it's a signed integer, remember, and you go from 1 to x, you compute the result, and then you return the result. Right? Now, what do you think should be? So precondition should always be x has to be non-negative, right? So this is my precondition. What should be the post condition? The problem is that if I again try to repeat the same code and try to compute the result, then actually it will match. It will match with the result, and you might think that, okay, the post condition is satisfied. But you won't be able to actually detect that. So let me first run this code. Right, so this factorial, and you can see that at line number 17. So this is a very basic post condition which says that the result, the factorial has to be greater than the number itself, greater or equals. It is failing at line number 70 for the 17. So this is my main where I try to compute factorial from 0 to 100. Right, so for 17 it is failing. Does it mean that this kind of overflow has happened only at 17? I mean, if you are observant, you will notice where actually things have started going wrong. It's just that you are not detecting. So ideally, so now sometimes you have to think about what is the other way to try to compute the same thing, or at least try to get that whether the desirable property holds at the post condition, right? So let me, I think, not waste time, and I'll tell you that I can do let's say x is equal to 0. If x is equal to 0, then what you want is that result is equal to 1, right? That's what you want. Or if x is not equal to 0, then what you want is that is the whole purpose of this previous result. I mean, why do I have this extra variable where I first assign previous result to result and then I compute this one? The whole purpose of this new variable is so that I can relate it how I am progressing with this, right? So now you know that if it has overflown, this condition would be violated, right? Because if you try to divide the result by previous result should exactly be equal to x. If it has overflown, most probably it won't be the same, right? So let me now, with this modification, let me run. Yeah. So now if I run, you see that it has precisely detected where the overflow is happening. That for 13 factorial, this particular condition gets violated, and that's why it's saying that post condition does not hold. Right. So two things. One thing is that you should not try to repeat the same thing that you are doing in the actual computation, because whatever the problem that might happen in the actual computation, the same thing might happen even during the contract checking. So try to use an alternative mechanism to see that the desirable property. And many times checking something is easier than actually computing something, right? So contract need not always pose as much of a computational overhead, even when you are doing a dynamic contract checking. But yes, it does have some performance overhead, right? And now I move on to the last and the third example. And this is very, I think, extremely desirable. It's not there in C++ by default, but languages like D and IFIL and other languages have. So when you define a class, right, what you want is you want a class invariant, that what particular property that an invariant should have, right? So I have defined a bunch of classes in this code. All this code will be available. I think the CppIndiaCon will post the links. It's available on GitHub. These examples you can play around. So I have defined points which take any floating point, two floating point x and y coordinates. If I take 3 points, it's a triangle, and I define an isosceles triangle, right? And let me first run this code, and I'll show you what happens, right? I hope the screen is visible. So first, I'm printing all three coordinates of the triangle, which are these three. Then I'm translating. It's a 2D grid translation. So all the points gets translated. So origin is changed to this point. Then I'm rotating pi by 6, and then I'm scaling by 1.5. Right. Now, how about what you want to first define that if it is an isosceles triangle, it does not, it retains the being isosceles triangle, that property it should retain under translation, rotation, and scaling, right? So that's the invariant that you want to specify. And that's what writing contracts actually give you. So just like concepts put constraints on the type, the contracts actually puts this nice constraint, which are actually, you know, whenever you try to model some real life or the mathematical objects. So the way I can do that, so right now the contract checking is disabled, right? Now let me just enable contract checking. So let me build with contracts. So now I built my program with contracts, and the first thing that will happen is that the precondition at line 98 is failing, right? So now what is that line 98, right? Let's see. So this is now the contracts check is enabled. It's a conditional compilation. So this is just a check of the triangle inequality. That first of all, if I am creating a triangle and giving 3 points, does it satisfy the triangle inequality, right? And those, I mean, if you are observing, you will notice that the original input, this is not a triangle. This is just 3 points which are collinear on the same line. So you can, using contracts, you can actually specify that, hey, look, you know what, you are not even specifying the triangle. So this is failing at a constructor. So there is a mechanism by which you derive from the special class so that you can, at the constructor time itself, before the constructor is invoked, you can check that whether this triangleness property is satisfied or not. Right, so that is one. And now let's say that, okay, let me make it a triangle. So this is 0 0, and then let's say that this is right, and yeah, so now this is a triangle, okay, and I'll compile this once again with contract. So let me again run with contracts. And now it says that, okay, so it says that the precondition at line number 160. So now there's another contract gets violated, right? At line 163. So let's see. So at 163, what am I checking? What I'm checking is that because I want to specify isosceles triangle, at least the two sides should be same, right? The third side can be anything, but there should be at least two sides which measure the same. And that is what I'm checking over here. This close enough is a function because these are floating point numbers. That's why I'm not really using equality, but I'm saying that whether they are close enough. Close enough is defined as essentially if it is less than this epsilon, then it is close enough. I think it is here. Yeah. Right. So this is definition of close enough. That the difference between these two floating point number is less than some precision, then I'll say that they are equal. So this is the nice thing, that especially the class invariant, many times you write classes that reflect some real life entities, etc. And the contracts gives you a way to define this property that, okay, what it is. So just like concepts give you this sort of, you know, the idea that your type has to satisfy this thing. Similarly, the contracts tell you that if it is isosceles triangle, it has to have this property. So the first thing is that this was failing at the constructor time, but now let me compile again. So now I am giving actually the isosceles triangle. And what I'll do is that there is a translation and scaling and rotation. So let me actually now change something, okay? So, or let me do this, right? So this was the actual code that I had written for the rotation, right? This code is incorrect. I'll leave it to you to sort of figure out that why this code is incorrect. So let me comment out this code. And it is actually the contract that helped me figure out that, there is something wrong here. And yeah, so this is incorrect implementation of rotation. So even though I constructed an isosceles triangle, but if it is not invariant to these operations, you know that something is wrong, right? So let me just compile once again. Task with contract. Right, and now if I do that, now it says that the exit invariant of this thing, again, better diagnostic could help, but at line 185, there is another contract, which is this one. That again, the being isoscelousness property that gets violated. And as you can see, that upon entry, my distances were 1, square root of 2, and 1. But after the rotation, what has happened is that these distances have sort of change, right? This distance should not change. Even if you rotate the triangle, the distance between these points does not change. So it's an incorrect implementation. So that is how the you can give these constraints as construct, that what it is to be isosceles triangle. There is no other way to describe but to actually put these constraints, right? And I'll change it. So the problem is that here, if anybody is curious, that I'm modifying p1.x over here, and then I'm using the same p1.x over here. So that's the problem. And this, with all three, there's the problem, right? So it should be the old x and y coordinate that should move to the new coordinates. So, and it is because of contracts, I could figure out that, okay, the problem, things that are going wrong, these things are wrong over here. So now if I comment out this one and if I do it this one, so essentially Boost contract library, they provide you these mechanisms. So for example, you can write a public member method called invariant. So this invariant will be checked upon entry of all public methods and upon exit, right? So that's what a class invariant is. So this property that whenever you do these transformations like translate, scale, rotate, etc., at all times you need to maintain these distances, right? So that's what it is like. I mean, these contract. And one other note is that, see, the problem is that even with this, I mean, you don't have thread safety over here, right? Because as I said, that ideally you want a snapshot and then you read the state. But since you cannot do it automatically, if it is a multi-threaded environment, and if you have a shared state, then even if your precondition during the dynamic checking, the assertion does not fail, it does not mean that actually precondition hold. And same with the postcondition, right? So the static checkers can actually do that because it is static. They have a way to sort of read the state at a given instant, abstract time instant, etc. But in the dynamic contract checking, you can't do. But now, like, does it mean that this is all useless? So let me just again go back to this one. I hope that slides are visible again. Yeah.
Yes, slides are just that we are out of time, but can
Yeah.
we finish
So
in
yeah,
one
this is
minute,
anyway.
please?
I'm just at the end, right? So even in the dynamic contract checking, just like testing, the absence of bugs are not really guaranteed. But very much upside is that it is a formal and unambiguous in-source documentation. Not only that, it's a self-documenting code in a sense that whenever you change the code, which changes the pre and post condition, the contracts will fail, right? So you will be forced to write the precondition and post condition, which is in compliance to your code. So that is another upside. And also the fault localization. So even in the testing, if you have a million line code, and even if there is a failing trace, there is a whole research area just on the fault localization. But if you have these contracts at various program points, you know that you can localize very quickly that where things have started going wrong, right? So the moment things start going wrong, it will fail. So these are, so even with unsound nature of dynamic contract checking, where the safety is not guaranteed, they are still not very, very much useful. And if you write contracts, it is helpful to the steady contract checkers, because our biggest regret is that programmers don't write contracts. So we have nothing to check the safety against. Now, with that, I leave you to sort of, read this statement. Like many times people say that, what you disable the contracts because of its performance overhead in the production. And this is the quote by the Turing awardee Sir Tony Hoare himself. Right. And with that, I thank you all. And I think I'll just leave this quote over here. And yeah, so thanks you very much for listening. If there are any questions, I would be happy to take it.
So thank you very much for the talk. You're worrying about values when in the concept side, I worried about the types. So that's good. We have lots of questions, I guess, but we are out of time. Can we take all of these questions in the chat, please?
Sure. Yeah, I'll be available on
Yes, please.
Discord.
So there is a dedicated thread for questions for you. So thank you very much for the enlightening talk. We certainly are shaken on the correctness of our programs now. We should think twice next time we write any code. Thank you very much and see you later.